Leak Detection System Tutorial Part 4. Implementing a leak detection system, LDS, requires careful coordination between system design, hardware integration, software configuration, and operational readiness. A successful implementation begins with clear assignment of responsibility. Ideally, the LDS should be developed in parallel with the supervisory control and data acquisition SCADA system, using the same supplier or integrator. This integrated approach streamlines factory testing, commissioning, and lifecycle support, while avoiding compatibility issues between separate platforms. When responsibilities are split between different vendors, strict interface and data exchange specifications must be enforced. Performance specification is the backbone of any LDS implementation. It defines what the system must achieve in terms of sensitivity, false alarm rate, detection time, and leak location accuracy. These parameters should be negotiated early in the procurement phase and validated during testing. A leak sensitivity study is often conducted to establish realistic performance targets based on pipeline characteristics and instrumentation quality. Incentive-based contracts that link milestone payments to verified performance outcomes, such as the successful simulation of a leak scenario, can motivate suppliers to meet agreed standards. Instrumentation plays a pivotal role in system performance. The accuracy, stability, and placement of pressure, flow, and temperature sensors directly affect the LDS's ability to detect leaks and reject false alarms. Instrumentation specifications should be reviewed with the LDS supplier to ensure compatibility with the detection algorithms. Where high performance is required, analog to digital conversions should offer at least 12-bit resolution, and care must be taken to minimize signal noise and latency. Thermal effects from solar exposure should also be mitigated through insulation or subsurface sensor placement. Factory acceptance testing, FAT, is essential to verify the functional and operational readiness of the LDS before site installation. The FAT should simulate realistic pipeline conditions using recorded or synthetic data to validate sensitivity, response time, user interface behavior, and communication with the SCADA system. A documented FAT procedure must be approved in advance, and results should be witnessed or verified by the principal. Pre-FAT testing by the supplier is recommended to identify and resolve any issues early, ensuring smoother final acceptance. Data sampling rate is another critical implementation detail. LDS software relies on high-resolution, time-aligned data to detect subtle deviations in flow and pressure. The SCADA or telemetry system must provide data at a rate compatible with the LDS requirements, typically once per second or faster for high-sensitivity systems. Sampling rates that are too slow or inconsistent can impair detection performance, increase false alarms, or obscure transient events that indicate a leak. Alarm management must be carefully configured. Leak alarms generated by the LDS are advisory in nature and should not directly trigger automated shutdowns unless validated through secondary systems like smart LBVs. Manual operator intervention remains the standard response, ensuring that human oversight governs critical decisions. Alarm thresholds, filtering logic, and display integration must be designed to minimize nuisance events while preserving timely and actionable alerts. Operator displays are vital for interpreting LDS outputs during both normal operations and leak events. Displays should present flow, pressure, imbalance, and inventory data in graphical form, preferably trends and profiles that are easy to understand at a glance. Overly complex or tabular presentations should be avoided as they can overwhelm operators during time-sensitive situations. Where the LDS is separate from the SCADA, consistent symbols and interface conventions should be maintained to avoid confusion. Operational procedures must align with LDS functionality. Consistent startup and shutdown sequences, adherence to instrument maintenance schedules, and well-rehearsed leak response actions significantly improve detection accuracy and reduce operational uncertainty. Regular blind trials where simulated leaks are introduced without notifying operators help validate system performance and readiness. These trials should be conducted annually to ensure familiarity and confidence in the LDS. In summary, the implementation phase transforms LDS design from concept to operational reality. Success depends on close collaboration between engineering disciplines, early definition of performance criteria, rigorous validation, and operator engagement. When properly implemented, the LDS functions as an integrated safety layer, enhancing the pipeline's resilience, improving response to unplanned events, and fulfilling critical regulatory and environmental obligations. Leak Detection System Tutorial Part 5, Leak Detection Techniques. Leak detection techniques can be broadly categorized based on the principle of operation they employ, ranging from simple flow balancing to advanced signal analysis and offline inspection methods. The choice of technique directly impacts the system's sensitivity, reliability, robustness, and response time. No single technique is universally applicable, and in many cases, a combination of complementary methods may be required to achieve the desired leak detection performance across varying pipeline conditions. Mass or volume balancing is one of the most widely used approaches, where flow entering and exiting the pipeline is continuously monitored. A discrepancy between the inlet and outlet flow, once corrected for pressure, temperature, and inventory changes, can indicate a leak. This method is effective under steady state and transient conditions and can detect small to large leaks with reasonable sensitivity. Corrected balance methods that account for line pack and temperature changes offer better performance than simple uncorrected balance techniques. However, these methods generally lack precise leak location capability. Statistical Pipeline Leak Detection, SPLD, builds upon the flow balance principle by applying statistical filtering and pattern recognition to distinguish genuine leaks from normal process variations. Developed by Shell, SPLD is particularly noted for its high robustness and low false alarm rate. It interprets leak probability based on correlated deviations in pressure and flow, making it effective in noisy or transient environments. While it does not require complex modeling, it offers reliable detection and rough leak localization, typically within 5% of the distance between sensors. Pressure and flow analysis techniques leverage changes in pressure gradient or flow profile to identify leaks. For example, a significant leak will cause a detectable drop in pressure upstream and altered flow conditions downstream. These methods are relatively simple to implement and do not rely on advanced modeling. Techniques like pressure point analysis can be cost-effective but are prone to false alarms during normal transients unless carefully configured. Location estimation is possible where multiple sensors are installed along the pipeline. Dynamic model-based methods use computational fluid dynamics to simulate the real-time behavior of the pipeline. These models solve equations for mass, momentum, and energy conservation to predict pressure and flow values, which are compared against actual measurements. While theoretically powerful, dynamic models have historically proven difficult to implement due to sensitivity to tuning, high false alarm rates, and complex maintenance. Their high cost and limited reliability under real-world conditions often outweigh the marginal gains in detection sensitivity. Wave alert and acoustic-based techniques detect leaks by analyzing pressure waves or acoustic signals generated by the sudden release of fluid. Negative pressure waves travel at the speed of sound and can provide rapid detection, often within seconds. If detected at multiple locations, the leak location can be triangulated. However, these systems are sensitive to noise and operational transients, often requiring high thresholds to avoid false positives. This reduces their sensitivity to smaller leaks and limits their use to sudden, high-rate leak events. Hydrocarbon sensing cables and sniffer tubes are examples of physical detection methods placed along the pipeline. These systems detect the presence of escaped hydrocarbons by changes in the electrical or chemical properties of a cable or by analyzing vapor samples. They offer high sensitivity and precise localization, often within meters. However, their application is typically limited to short pipelines or high-risk sections due to high installation and maintenance costs. Offline techniques such as static pressure tests, leak detection pigs, and aerial or ground patrols offer alternative detection methods when the pipeline is not in active operation. Static pressure tests detect pressure decay over time in an isolated segment, while ultrasonic pigs identify acoustic signatures of leaks during an inspection run. These techniques can detect very small leaks, but are inherently periodic and do not offer continuous surveillance. Remote sensing using drones or infrared cameras is also gaining traction, particularly for difficult to access or environmentally sensitive areas. Each technique has unique strengths and limitations. For instance, balance methods are robust and broadly applicable but lack location precision. Dynamic models promise comprehensive coverage but demand intensive tuning. Acoustic systems provide fast detection for sudden ruptures but are less effective for small or gradual leaks. Physical sensors offer pinpoint accuracy but are costly and limited in coverage. Therefore, the final LDS design often involves layering multiple techniques to capitalize on their combined benefits. In conclusion, the selection of leak detection techniques must be tailored to the pipeline's characteristics: fluid type, operating pressure, environment, and risk profile. A thorough technical and economic evaluation should guide the deployment of one or more techniques to ensure optimal detection performance. Ultimately, the chosen methods must balance speed, accuracy, cost, and reliability to form a system that supports safe, compliant, and efficient pipeline operations. Leak Detection System Tutorial Part 6. Monitoring of characteristic signals generated by a leak. Certain leak detection methods rely on the distinctive physical signals produced at the moment a leak occurs. These signals, such as sudden pressure drops, acoustic emissions, or changes in wave propagation, can be used to detect the initiation of a leak event rapidly and, in some cases, even pinpoint its location. These techniques are often used to supplement flow or pressure balance methods, providing an additional layer of detection that focuses on the leak's onset characteristics rather than ongoing mass imbalance. Negative pressure wave detection, commonly referred to as the wave alert technique, is one of the most established methods in this category. When a leak occurs suddenly, especially under pressure, it generates a rapid drop in pressure at the leak site. This pressure drop propagates both upstream and downstream at sonic velocity. Sensors positioned along the pipeline detect the arrival of these waves, and the time difference between detections is used to estimate the leak location. Due to the speed at which the wave travels, often exceeding 1,000 meters per second, this method offers extremely fast detection times, often within seconds of leak initiation. The accuracy of wave-based systems depends heavily on sensor spacing and response time. With adequate instrumentation, leaks can be localized within approximately 1 kilometers of accuracy. However, practical performance varies with pipeline length, fluid type, and background noise levels. While highly effective for sudden and large volume leaks, negative pressure wave detection is less sensitive to slow developing or pinhole leaks, which may not generate sufficient pressure disturbance to trigger a detectable wave. To improve signal clarity and reduce false positives, dual transducer systems are often employed. These systems use two pressure sensors placed at a known distance apart to differentiate between legitimate leak signals and ambient noise. Directional signal processing can suppress interference from upstream or downstream operations, increasing the reliability of detection. This selective filtering is critical in noisy environments, such as near compressor stations, pump houses, or turbulent flow zones. Despite their advantages in speed and location accuracy, wave alert systems have limitations. One key constraint is that they respond only to the initiation of a leak. If a leak develops gradually, or if the initial pressure wave is missed due to sensor failure or noise masking, the system may not detect the event at all. Therefore, wave detection systems must be complemented by continuous monitoring techniques such as SPLD or corrected volume balance to provide persistent leak awareness beyond the initial signal. Acoustic leak detection is another approach that monitors high-frequency noise or vibration patterns generated by fluid escaping through a breach. These emissions, often ultrasonic, can be picked up by specialized sensors clamped to the pipe surface or embedded in the pipeline infrastructure. This technique can be effective in detecting both sudden and slowly developing leaks, particularly in liquid pipelines under pressure. The main advantage is its sensitivity to the turbulent noise generated by high-velocity fluid jets escaping through small holes. However, acoustic systems typically have limited range, often only a few hundred meters per sensor, and are more commonly used in localized high-risk zones rather than along an entire pipeline. Applications include offshore risers, terminal manifolds, and critical urban crossings where leak response time is paramount. Careful calibration is required to differentiate leak signatures from operational noise, valve chatter, or mechanical vibrations, which otherwise lead to false alarms. Hydrocarbon sensing cables offer a passive signal-based method of leak detection. These polymer-based cables change electrical properties when exposed to hydrocarbons, triggering alarms when a release comes into contact with the cable. Unlike wave or acoustic methods, these systems detect the presence rather than the initiation of a leak. They are highly effective in pinpointing leak locations within a short range, typically less than 100 meters, but are costly to install and maintain over long distances. As such, their use is usually reserved for areas where leak consequences are especially high, such as tank farms, jetties, or environmentally sensitive corridors. Other specialized techniques, such as optical sensing or infrared-based methane detection, may also fall into this category. These systems monitor for changes in specific gas concentrations or light absorption patterns and are often deployed via drones, mobile platforms, or fixed installations. While still emerging in commercial deployment, these technologies offer promise in detecting gaseous emissions in open air or subsea environments where conventional instrumentation may be impractical. In conclusion, monitoring for characteristic signals generated by a leak adds valuable speed and localization capabilities to a pipeline's leak detection strategy. These methods are particularly effective in detecting fast-acting, high-impact leak events. However, their limitations, such as narrow sensitivity windows, high installation costs, or susceptibility to background noise, mean they are best deployed as part of a layered detection architecture. When combined with flow, pressure, or statistical techniques, signal-based systems provide a robust and responsive defense against uncontrolled fluid release.